Here we're going to talk about shear stress and strain in our next video. So we're just going to talk about the basics and explain what that really is. Again, when we talk about stress and strain, the definition of the ratio stress divided by strain in this case is going to be equal to what we call the shear modulus. So let's write that down. Shear modulus, which is the measurement of the property of a material related to the shear stress and the shear strain. We don't know yet what it is, but hang with me. Again, shear stress is force divided by area, so that hasn't changed. What do we call the shear strain? Well, to illustrate that, I have a little drawing right here. Let's say we have a big block of some sort of material. Let's say that we anchor one part of it down on the ground like here. We nail like a 2x4 down here so that this can't move. And now we go ahead and push on the material in this direction. Well, what will happen is this material will deform. And how it will deform is that this top portion of it will be pushed to the right, and because the bottom portion here cannot move, it'll stay in place. And what we find is that this will deform like this, and the material will, in a way, bend kind of like this. I'm hoping that becomes clear. My drawing skills aren't the greatest, but you can see that the top portion of the material has moved over a distance like this, and let's call this distance, let's say, call it delta x. A certain amount of deformation of the top portion of material where the bottom portion of material is not deformed at all. And of course, it does depend upon the height, h here. If this height is very small, then delta x will probably be very small as well. If h is very large, then delta x can be proportionally much larger as well. And of course, the amount that the material deforms like that will depend upon what we call the shear modulus, which is the strength of the material in this particular fashion. So therefore, the shear strain cannot be defined as, you've probably guessed it, the amount of deformation in this direction right here as a function of the height of the material. So this will be delta x divided by h. And this here is the ratio of shear stress divided by shear strain, which is defined by the strength of the material as being called the shear modulus. So we're going to call this equal to S. And that's simply the ratio of the shear, and I'll write it down again, shear stress divided by the shear strain. Now, materials that are really strong, that have a very high shear modulus, you can push on really hard and they will deform just a very small amount. Metals, for example, will probably fall in that category. And even wood, you have a big wood block and you push on it really hard this way and hold it back here, it's not going to deform very much. Now, of course, you have some other material like a soft plastic or a foam or something like that. You push on like this and it will deform quite a bit. So those have very small shear modulus. Notice that F divided by A, if that ratio is very large, so if that's a really large force divided by a small area, then you expect a large deformation. Unless, of course, the material is really strong. If the material is really strong, then it requires an enormous amount of force to cause a small deformation. So that's really a good way to look at it. Another thing that's different about the area is that the cross-sectional area is the top portion of it, is the surface on the top. And so sometimes it's really hard to visualize. So let me show you some examples where in industry, this is really an important factor. So let's say we have a steel plate that looks like this. Very large steel plate, and it's not very thick. And let's say we want to come with a big machine and cut a piece off. So let's say we have a big machine like this, and want to apply a lot of force in a downward direction and lop a piece off. So cut this little piece off like that, so we end up with a piece taken off that looks like this. Now, of course, how easy is it to do that? Well, that depends on the shear modulus of the material. If this is a very strong material, you need to apply a lot of force. But how does the delta x and the h and all that how is that taken into account? Well, notice that if you look at the other side where the material is being cut off, like so, then you can see that this here becomes the cross-sectional area of the material that's sheared. Notice that what you're going to do is, when this is still attached, you're trying to push this material away from this material, so you're going to try to stress it in this direction. So it's basically stressing it like that, and so the cross-sectional area is simply the cut-up area, or the cross-sectional area of the cut becomes the area here. So the important part of an industrial application like this is to just understand how much force will be required to go ahead and cut a piece of material off. And so what we're looking at here is the limit of that material, and that's usually defined by the maximum shear stress it can withstand. So in this case, we're looking for the shear stress max that the material can withstand, and that's going to be equal to the ratio of the force divided by the area. In this case, the area will be the cross-sectional cut of the material, and the force is the force applied to do that. So once you know the shear stress of the material, you multiply times the cross-section area, and then you can calculate how much force you need to do that. Another application in industry where this is important, if, for example, is where you try to punch out a hole out of a material like this. Let's say you have a metal sheet, and you want to punch a hole in it. So you come with a big punch, and you come down, you apply a certain amount of force, and the question is, how much force does that require in order to punch out that material? Well, when you see the piece that was punched out, you're left with a hole. So let's draw this again over here. And then you're left with a hole, and the hole will probably kind of look like this. Not quite. Let me try again. There we go. That's a little better. So that's what the hole would look like. And notice that you have a radius of the hole, and you have a circumference of the hole, where the circumference of the hole is equal to 2 pi times the radius. And then you have the height or the thickness of that material. So it turns out, again, the area that we're interested in, the cross-sectional area that we're interested in, is simply the area left by the side of the hole. So if you say, well, this is the thickness of the material right here, let's call this T for thickness, then the area here would simply be the circumference of the hole, 2 pi r, and you multiply it times the thickness T, and that now gives you the cross-sectional area of the cut, which would be kind of the same as the cross-sectional area of the cut here. And again, when you talk about the shear stress of a material, it would be the force required to punch a hole through there, when the leftover area along the sides of that hole would be equal to A, which is equal to the circumference, 2 pi r, times the thickness of the material. And so that's a good application of the shear modulus. In the next couple of videos, I'll do some examples of how we calculate the shear stress and the force required to cut or cut holes through material.